And there is a great interest is that you can tune the property of your nanoparticles. For example, you have here colloidal solution, so homogeneous solution with nanoparticles. In each one of those bottles, you have the same nanoparticles with the same materials, the same size. But due to the change in size of the nanoparticles, you will have drastic difference in the optical property of these particles. And so it has some very great interest for application. But also for fundamental research, because investigating the property and the mechanism for single nanoparticle can give you information about phenomena at the nanoscale, for example, thermal transport. And today we have a very large diversity of nanoparticles that can be synthesized, metallic, semiconductor, but personally I'm more interested in metallic nanoparticles. And in the field of nanotechnology, one very famous example is the Le Corbusier cup, which is a cup made about 17 centuries ago, which is made of glass with some gold and nanoparticle embedded in the glass. And due to the plasmonic properties of those metallic nanoparticles, it will have a different color if you light the glass from within or outside, from the front or the back of the glass, due to the particular properties of those nanoparticles. So it's some kind of example of Roman nanotechnology. And so, since for the last 2-3 decades, a lot of research have been done and have been realized in the property of nanoparticles, from the optical property to the elastic properties. Especially when we are working on metallic nanoparticles, we have a lot of research have been done, and it happens that ultra-fast FEM probe spectroscopy is one of, so FEM probe techniques is one of the, have proven to be a very efficient way to investigate the elastic properties and the vibrational response of such nano-objects. And so it has been used to investigate a large number of material, shape, or size. You have here 3 examples of gold nanoparticles with nanocube, nano-octide, and nano, I don't remember how many faces, particles. And it has also been investigated in a number of different environments, from air, liquids, or in contact with different substrates. And one of the interesting things about this kind of nano-object is that you can describe them with a macroscopic-like description. So basically, if I show you this model shape, if I don't give you the frequency, you are unable to distinguish, to determine if it's not the gold nanoparticle, a basketball, or the Earth. And so we can use macroscopic-like theory and continuum mechanics down to around 1 nanometer. So even for particles, which you can basically count the number of atoms, I think the recording was something like 1.3 nanometers. So it's for a nanoparticle made of gold, it was something like 75 atoms of gold. You can still describe it just like you would describe any material and every object in this room. And so, of course, the modes of the nanoparticle will depend on shape, size, and material. And since the frequency is inversely proportional to the size, you will obtain a resonator with resonance and frequency in the gigahertz or even terahertz wave range. And one last point, but very interesting, is that it has the environment has a huge impact. There is a great coupling between a nanoparticle and its environment. And so we can take advantage of this coupling. We can consider the nanoparticle as nanoresonator and then investigate the change in frequency or damping for different environments. This is what have been done, for example, in the team of Gregory Hartland in the USA, when they investigate the vibrational response of nanowires or nanoplates in different liquids, and looking at the difference in frequency and damping, they can determine the elastic property of liquids at the nanoscale. Another recent application is to put some polymer between different nanoparticles and to investigate the response of the systems. So you have basically a mass spring systems, and you can determine the mechanical properties of the polymer used. And so I assume that in a couple of years, they will be able to even determine the mechanical property of single molecules using such techniques. And so there is a lot of other applications based on the resonance of nanoparticles, from mass sensing to optomechanics. And so there is a lot of people interested in those nanoparticles and the properties. And another application and advantage you can take from the coupling between nanoparticle and its environment is to use nanoparticles as nano-source, an acoustic source with nanometric dimensions. It has been shown that that nanoparticles can emit acoustic waves. Acoustic waves that can be associated with the vibration of the nanoparticles, and so which will have frequency in the gigahertz range, or even terahertz. And so, for example, Kelf has shown that some nano ring made of gold can generate acoustic waves. Some nano plates, nano disk can also generate transverse wave. And more recently, IMAD has shown that you can even use nanoparticles, in that case, nanowire, to generate surface acoustic waves. And so the idea for my PhD, I skip a step. And so usually what you want to generate very high frequency, you use Picosecond acoustic techniques, which are based on the absorption of a laser pulse to generate gigahertz or terahertz waves. And so you can use this technique to do some acoustic imaging. Two of them that you might know here, two examples that you might know because they were performed here at the LOM. Another one is a elastic cartography of some neuron-like cells, which are compared here with a fluorescence image. So you can deduce the mechanical property of a single biological cell. But using those techniques, there is some limitation. For that, I will distinguish axial resolution and lateral resolution. So the axial resolution is the resolution you can obtain along the axis of propagation of your acoustic waves, while the lateral resolution will be in the plane. And so, of course, this resolution will depend on the optical property of the material and of the light source. So basically, the axial resolution will depend on the wavelengths and to the penetration length of the light in the material, while the lateral resolution will be limited by the size of your source and receptor. So basically to the size of the laser. And due to the diffraction of light, you can't reduce the size of the laser spot to an infinitely small size. You are limited to a size which are of the order of the optical wavelengths, so a couple of hundred of nanometers. So you can't have a lateral resolution that are smaller than that. So over the last years, different approaches have been explored to do acoustic imaging with a better lateral resolution. One of the propositions was to use some acoustic lens to focus the acoustic field after the generation by the acoustic, after the absorption of laser pulse. But in that case, we'll lose the non-contact advantage of Picosecond acoustics. Another proposition was to do some coupling with some near-field optical microscope, and they were able to reach a lateral resolution of about 100 nanometers, so better than what you can have with a single laser. And a third approach is to use nano-sources, such as nanoparticles, so source and receptors with much smaller characteristic dimensions. And so during my PhD, that was kind of the goal, to find and to investigate nano-source, so acoustic source with nanometric characteristic size, but that can still generate very high frequency in gigahertz or even above, and that can be easily tuned. And ideally, the goal is to implement such nano-source to do some acoustic imaging. And so I will present 3 examples of systems from a single nanoparticle to a nanostructures and to some, not really nanostructures, but structures with nanometric dimensions that have been investigated during my PhD. And so the first part is to I'm interested in the elastic characterization of a single metallic nanowires. Why is that? Because the previous PhD student who worked at the NSP on the vibration of nanoparticles has observed that when you take copper, a nanowire made of copper, put us on a silicon substrate, and you excite this nanowire with a laser pulse, you can observe an acoustic field in the silicon substrate. This field is emitted by the nanowire due to the vibration of one of its eigenmodes, is particularly the breathing mode of the wire, for which you can see the little shape here. And due to the particular size and shape of these nanoparticles, you can obtain an anisotropic acoustic field in the substrate. And since we can describe nanoparticles as macroscopic objects, we can easily describe the breathing mode of nanowire, considering it as infinite and made of anisotropic material by the Pochhammer Chree equation, which link the frequency of the different harmonics of the breathing mode with both the size of the wire, with A the radius, and the elastic properties of the material it's made of through the velocities. And so if you want to use nanowires as nano-source, we can easily tune the nano-source and the frequency by changing, for example, the radius of the wire. And so we have a large number of frequency we can have. Another way to modulate the frequency of the emitted wave could be to use harmonics, but unfortunately, the generation of harmonics and the emission of acoustic wave by the harmonics are not very efficient process. Another approach would be to change the material to have different elastic properties. For example, in this case, use gold or silver instead of copper. But we are still limited in the number of coupled frequency size. We are still limited, so we want to have more choice. So we can use nanowires and nanoparticles, which has heterostructures when we combine several material or several phases, and that will display some unique properties. But in that case, you will need prior to using those nanoparticles with unique properties, you need to be able to characterize those properties. And so in the case of nanowire, the proposed method is to use the breathing mode also. Indeed, if you can determine precisely the radius and you can measure at least 2 values of the breathing mode harmonics, you can solve this equation in order to determine both velocities in the same time. And so you will have a study that allows you to investigate the breathing mode of the wire as nano-source, but also to determine the characteristic elastic properties of the material. And so this can be done on heterostructure, but I will show you an example applied on purely gold nanowires. Those gold nanowires and other metallic nanowires I will very quickly talk about were synthesized in Germany at the JSCL mods by the team of Professor Tomil Morales. And they have a characteristic length of a couple of dozen of micrometers, even longer for some, with a very well-defined radius that you can easily measure using some SEM, so scanning electron microscope. And so very quickly, they were obtained using a template method and some electron deposition to have this particular characteristic size. And one of the important things when you are investigating the vibration of a single nanoparticle is, as I said, the environment of the particle. And so what is commonly do is to use restructured substrate. In that case, in our study, we use some silicon wafer in which we chemically etched some trenches. So as you can see on the scheme or on this image. So on a very large portion of the nanowire, there is no contact between the nanoparticle and the substrate. And since we are investigating breathing mode, so purely radial mode, we can assume that there is no energy loss for this mode in the substrate. And this is the experimental setup used to investigate such nanoparticles, the classical two-color FEM probe experimental setup, when we have two laser beams with two different wavelengths, one that will one laser will be used to excite the nanoparticle, and one to detect the variation of optical properties due to the vibration. So in that case, we use a pump at 400 nanometers and a probe at 800 nanometers. And so using this kind of setup, this is the typical transient reflectivity that you can measure on a single nanowire made of gold above the trenches with a nominal radius of 100 nanometers. And so we can observe large oscillation for a long time for nanoparticles, in that case more than 6 nanoseconds, with and the spectrum of such signal display several components of a large range of frequency from 5 gigahertz to almost 50 gigahertz, and thus as the information we're interested in, because every single one of these components correspond to an eigenmode of the nanowire. In particular, the first component F1 can be associated to the quadrupolar mode of the wire, for which you have the model shape here, while the component F2, F3, and F4 can be linked to breathing modes and harmonics of the wire. And so this as a value we want to use to determine the elastic property of the material. Because when we know those values, knowing also the precise value of the radius A, we can determine for each of those the couple of velocities, VLVT, that solve the Pochhammer Chree equations. And since we have several values, we have several curves of couple of velocities, and ideally, we would have a single intersection point for all of those curves that give you the physical values of the velocity. So due to experimental certitude and noise and things like that, we have in that case several intersection points, but with over a very small interval, especially of longitudinal velocities. The values of the transverse velocities are a bit more dispersed because breathing modes are less sensitive to transverse velocities than to longitudinal velocities. But in that case, we can determine quite easily the velocities of the materials the nanowire is made of. And so this has been applied to gold, but gold nanowire, but we can also use it to do to investigate some heterostructured nanowires. For example, nanowires made of an alloy of gold and silver, for which we can determine for different nanowire and for different composition of the alloy, both velocities. But this is not when considering nanowires as nano-sources, this is not exactly the perfect example because silver and gold have quite similar elastic properties. So the variation of the breathing mode frequency is small, but we can also investigate more complex structures. For example, nanowires made of porous gold. In that case, we don't change the radius of the nanowire, we don't change the material, but we change the porosity. And it will lead to a drastic change of the frequency of the breathing mode, which is quite interesting if you want to develop application based on such nanoparticles as nano-sources. So we have an inverse method allowing to determine the elastic properties of nanowires. And here I show some examples performed on metallic nanowires and nanowires with heterostructures, but we can also investigate nanoparticles with, for example, semiconductor material covered with a layer of metal. And so we have access to a huge number of nanoparticles to develop application that. But are nanowires good nano-source? Well, we have an acoustic source that allows to generate very high frequency that can be tuned and with a source with nanometric size. But the issue for such nanoparticles is that you don't really control the position of a nanowire on your substrate. Classically, what we do is we have a huge number of nanowires in a solution, and we put a droplet of the solution on the sample, and we let dry. So basically, we have hundreds or thousands of nanowires on the substrate and with quasi random distribution, and we hope that one in the right position for a study. So what we investigated in the second time was to use nanoparticles made by photolithography, so we could have a very good control of the position of such nanoparticles. That was the case in the second part when we investigated gold nanodisk. So the structure we consider here are gold nanodisk, which are synthesized by photolithography directly in the clean room at the NSP. And so we have, as you can see on this image, a very good control on the position, but also on the size of the particle. And we have the characteristic size of such structure are a thin thickness of 100 nanometers, in that case, for a large radius of around 1.7 micrometers. The difference in the of one order of magnitude in those two dimensions will allow to separate easily the eigenmodes of the structure associated to the thickness or to the radius of the particles. And one thing we can do is to do some wet chemically etching of the silicon substrate on which we synthesize the nanoparticles in order to obtain a silicon cone under the disk. And so we obtain a nanodisk which is partially in contact with the substrate. And so later we'll use the value Rg, which is the etching radius. So it corresponds to the part of the radius of the disk that is not in contact anymore with the silicon. And so the experimental setup used to investigate such structure is similar to the one used to investigate nanowires, except that we had a Michelson interferometer for the detection, because it will allow us to have to be sensitive to the normal displacement at the surface of the disk. And so we have two setups, one in reflection, when both pump and probe laser are focused on one side of the sample, and in transmission, when we focus on each side of the sample. And so this is the typical time resolved response that you can measure on quite a long time, 10 nanoseconds, on a single nanodisk made of gold, without any etching for the moment. And so you have here a peak corresponding to the absorption of light, which changes the optical property of the gold. You have a slow variation due to the rise in temperature and cooling of the gold, and you can observe also some oscillation after around 1 nanosecond here. And if we extract those oscillations and look at the spectral components, you can distinguish 3 different components. Just like for nanowires, we can assume that we can determine that each of these components can be linked to one of the eigenmodes of the disk. But since there is a contact with the substrate, it's a much more difficult geometry. So we can use numerical simulation in order to investigate those modes. For that, we developed a model based on using COMSOL, as commercial software, using some finite element simulation. And this is a geometry considered. So we have the disk with the substrate, which can be considered as infinite using some PML layer here, and with an adaptive size of the substrate to limit the cost of the computational cost. And what we can obtain with such model for a nanodisk without etching, we look at the normal surface normal displacement on top of the disk, and we can obtain such spectrum with 3 components with frequency relatively close to the one obtained experimentally. And each one of those components can be associated to one of the eigenmodes of the structures. So since we have a good current results between the experimental results and the numerical, we can adapt the geometry to investigate what happens when we do some etching and we reduce the contact between the nanodisk and its substrate. Especially, we can look at how the modes are affected. And so for a large number of etching radius, we measure all the, we take all the values of the different eigenmodes, and we can link them by investigating similar modes, similar number of nodes and antinodes. And we can also take into account the two limit cases, which are a disk fully in contact with substrate and a disk completely free without any contact. And one can we observe with a simulation that the contact with substrate has two impacts. Firstly, the frequency will decrease, but also the if you increase the etching radius, the frequency will decrease, but at the same time, the quality factor of this different mode will increase. So the substrate acts as a relaxation channel and also as an apparent increase in stiffness. And so this numerical result can be also investigated experimentally. For that, we have done some measurement on disk with different etching radius. And the spectrum we can, and so for which of them we can obtain spectrum. In that case, we observe that for the two of them, we have several components with frequency much smaller than the one obtained in absence of etching, and with even smaller frequency in the case of a more important etching radius. We can also investigate the spatial dependence of the component we can obtain. So on the same disk for an important etching radius, if you do a measurement on the center or at the edge, we have similar components, for example, 0.3 or 0.6 gigahertz, but on the edge, we will also have additional modes, which once again tell us that the substrate acts as a relaxation channels. And the important thing and interesting thing is that all of the frequency we can obtain experimentally can be found also for the same values of etching radius numerically that show once again the good currents in the results. So this is the investigation of the vibrational response, but this is not exactly what we're looking at when we want to use such structures as nano-source. But if we look in the first nanosecond after the excitation, we can find some additional oscillations, which is a much smaller period, and that quickly decreases. And so if we extract those oscillations, we can reproduce them and deduce both the lifetime and the lifetime of those oscillation and its quality factors. And what we can deduce from that is that in that case we have a 16.8 gigahertz for a quality factor of around 5. And this additional oscillation can be associated with thickness mode period. So it will depend on two parameters: the thickness of the gold disk and the celerity of acoustic waves. And so if we take 100 nanometer and the velocity obtained previously on nanowires, we can find similar values for the period and the frequency. So just like for the radial mode, we can investigate the spatial dependence. And for the same sample, if we do measurement on the center and on the edge, we will obtain in both cases the similar frequency. But when we're looking at the edge, we'll obtain much longer lifetime for the mode and a much more important quality factors. And so to investigate much more this spatial dependence, we can do several measurements along the radius of a single nano disk. So in the absence of etching, we will have very similar value all along the radius with very few variation. But if now we consider etched sample, we'll have a much more important variation of the quality factor, even more important, reaching almost 70 compared to the 5, when you have a very important etching of the disk and of the silicon. And so we can also compare as limit case this result with the one we can obtain on the film that's fully in contact with the silicon substrate and on the membrane that is fully with completely in absence of contact. And we found, for the film, we found similar values for the quality factors and the one obtained for the disk fully in support 2. And in the case of the membrane, we have a very high value of the quality factor, for which the more important value obtained on etched disk is almost similar. And so to understand what that means, we remember that the quality factor can correspond to the ratio of energy stored to the energy lost per cycle. And so we can dissociate this quality factor to have one value associated to every process of energy loss. In that case, we distinguish the intrinsic phenomena and the coupling with the environment. And the environment can itself be decomposed in two parts: the silicon substrate and the air around the nanoparticle. Due to the important mismatch in impedance and the important impedance mismatch between gold and air, we usually consider there is no radiation in the result, and so there is no loss due to this coupling. And now, if we consider the particular case of the membrane, since there is no contact with silicon, the measured quality factor directly corresponds to the quality factor due to intrinsic phenomena. And so we have value for such process. And knowing the quality factor intrinsic, we can determine the quality factor associated with the contact with the silicon substrate. So in the case, if we take the average value obtained on a disk fully supported, we have a single value of the quality factor in the case of contact with silicon. And we can even use this value to determine the reflection coefficient from gold to silicon. And we obtain here, in that case, a value of 0.55, which is very close to the one expected using the acoustic impedance of both materials. But the very important thing is that we can observe that the quality factor associated with the silicon substrate is much smaller than the one associated with the intrinsic phenomena, meaning that this mode lost way more energy by radiation in the substrate than due to the intrinsic phenomena. And so to investigate this loss of energy, we consider the transmission experimental setup, when both pump and probe laser beam are focused on each side of the sample. And so if we look at the propagation, acoustic propagation, the silicon membrane here, we have all the transverse and longitudinal waves propagating back and forth in the silicon membrane. And we in particular can distinguish a step due to the longitudinal wave excited by the pump beam and detected by the probe beam on the other side. When the pump and probe beam are now focalized on the disk, we have different waves propagating. Especially if we look at the same temporal window, we will observe kind of a step, but we observe additional oscillations that were not seen previously. And there is also a delay due to the height of the silicon cone. And this oscillation can be extracted and investigated, and we will find a frequency, also a quality factor similar to the one obtained in the case of the thickness mode of the disk, proving that when the disk is vibrating along its thickness mode, it emits waves at the same frequency in the silicon substrate. And so we can do some acoustic cartography of the displacement field on the other side to look at acoustic waves coming from the nanodisk. And so basically what we have is a nano-source with tunable frequency that can be designed by choosing carefully both the height of the disk, the thickness of the disk, and the material, and so the velocity of acoustic waves in the disk. And so we have a tunable nano-source. And because the size of the source will be the size of contact between the gold disk and the silicon substrate, we can also have very small source size below the characteristic size of laser spots. And so we can have micrometric or nanometric size. And so basically what we have done here is we have investigated both the radial and thickness mode of gold nanodisk, and we have looked more particularly in the impact of the substrate on both of these category of modes, and both experimentally and numerically. And by investigating the quality factor of the thickness mode, we can have shown that acoustic emission in substrate by the disk. And so I kind of repeat myself, but we have a nano-source with tunable monochromatic acoustic emission. We control the size and the position of the disk, and we control the size of the source. And also I didn't show here for time reason, but we can also do the reverse experiment when we generate acoustic waves in silicon, and it will excite the nanoparticles and will lead to a richer spectrum. So it also proves that the nanodisk can be used as a nano receptor in addition to the nano source. The limit for such system is that you have to do some photolithography right on the sample to put in nanodisk. Plus, you need to do this etching phase. So it's not very applicable for a lot of systems, but maybe it can be. I think it can be used for some structural health monitoring at the nanoscale in electronic components, for example. So a third experiment done, a third approach done during my PhD was to do some coupling between atomic force microscopy and picosecond acoustics. So the acoustic and atomic force microscopy coupling already exists, but what they usually do is that you have the cantilever due to the cantilever of the atomic force microscope in contact with the sample, and thanks to some piezoelectric crystals, they are put in vibration either the sample, the cantilever, of both of them. So because they are using piezoelectric crystals, the vibrations are usually in the kilohertz or megahertz range, and they look at the variation of the contact force between the two due to the vibration, acoustic vibration. So this can be considered as low frequency example. Some work has also been done coupling picosecond acoustics. That, for example, in that case, when they use the pump beam to generate acoustic waves from one side of the sample, the cantilever of the AFM is in contact on the other side, and they use the probe to look at the vibration of the cantilever. And using such high frequency setup, the people were able to reach a lateral resolution of about 100 nanometers, so similar value than the one obtained coupling picosecond acoustics and near field optical microscopy. And so here we want to consider a new approach, ideally where there is absolutely no contact between the laser beam and the sample. For that, we use some AFM probes, which are this one, for example, which have two interesting things. First, they're covered with aluminum to generate efficiently, and they have a characteristic size at the edge, below 10 nanometers, so way smaller than what you can obtain with the laser spot. And so if we look at the acoustic propagation in the cantilever and the AFM probe in the first time, firstly, when we are focusing both laser beam on the cantilever, we can observe such response over 2 nanoseconds, which important peaks here that correspond to acoustic longitudinal acoustic waves that are propagating back and forth in the thickness of the cantilever. So using those peaks, we can come and determine every variation of thickness in the cantilever. So if we do a cartography before the peak, no structure are really observed on the back on the cantilever. But now when we do a new cartography at the time of the peak, the peak in question will be detected at every position with the same thickness, and every variation of thickness will reveal some structures. In that case, for that particular probe, we can detect some defects here that you can also see here. But also we can detect from the back of the probe the most important part for us, the edge of the peak. And so using this cartography, you can easily focalize from the back of the cantilever probe, from the back of the cantilever, the laser beam right directly on the position of the edge. And in that case, if we look at the propagation acoustics, because the thickness is way more important, the cantilever is about 2 to 3 micrometers in that case, while the peak is about 20 micrometers. So we don't see anymore the peaks due to the long longitudinal waves. But if we look carefully and we believe a bit, we can find some structures at much longer times. And this structure corresponds to acoustic waves that have been generated and propagated along the peak before being reflected. Okay. And so such propagation can also be investigated numerically. So there is no emission. Okay. So we have worked with one of our colleagues at the NSP, Daniel Garza Sanchez. We have coded some 3-dimensional simulation of the cantilever, taking into account the anisotropic silicon of the probe, to look at the acoustic propagation. And so we can distinguish, for example, the transverse verse as well as the longitudinal waves propagating along the FM probe. And we can investigate what happened when we have after the reflection and what the acoustic field inside the probe. In particular, we can see that there is some mode conversion. When the longitudinal wave is reflected, it will lead to a new longitudinal wave, but also some transverse wave. So this is an ongoing work, which is not totally finished. But why are we interested in that? Well, if we take the cantilever and we look for this particular cantilever as a response, you have a structure when we can identify easily 2 peaks named here A, B. And now we put the same cantilever, but in contact with some silicon parts. And we will observe a similar structures with A, B, but the intensity of the peak A is much less important. So the hypothesis for this, the explanation for this loss of intensity is that there is some acoustic transmission from the AFM probe to the silicon sample. And we can be interested in the sensitivity of the force we applied between the probe and the silicon. And so we did some measurement, and we observed that whatever the force we apply, we have a similar response in the case of the contact with the silicon. So the peak A always disappears. And this is the difference between the response obtained in contact and the response without the contact. And we can also be interested in what happens if we are sensitive to the material we're in contact with. In that case, we have a sample made of silicon which is partially covered with gold. And so if we do just an optical image with a laser beam, when we'll go from one of the material to the other, we will have a drop and edge due to the change in optical properties of the 2 materials. And the size and the lateral resolution will depend on the focalization and of the laser spot size. Now we can do follow a similar path using the AFM probe with the laser beam, and we look at the acoustic intensity before the echo associated to the longitudinal waves. In that case, we don't see any structures corresponding to the going from one material to another. But if we look carefully at the time of the peak A that we see a huge drop in intensity, we can find again this edge. because the intensity of this peak will be affected by the material in contact with the at the end of the probe. In that case, there is much more transmission when you have a contact silicon-silicon than when you have a contact silicon-gold. And so to continue to investigate this transmission, we can do just like for the gold nanodisk and look in transmission what's happening. And so we take a silicon membrane. We can look once again at the acoustic wave propagating back and forth in the thickness, and you can find again huge peaks due to longitudinal waves. And when now you put the FM probe in contact, and you have the probe, the pump beam focalizing at the FM, generating waves in the FM probe, and the laser probe on the other side of the silicon membrane, you don't see anymore those kind of structures, but you can detect, also believing a bit, an important peak going that can be associated with the longitudinal wave coming from the FM probe to the silicon membrane. And so this is a component that was not detected in the absence in the previous geometry. And so if we can do again this experiment when there is no contact between the FM probe and the silicon substrate, we don't see any structures, but when you use the contact, you will find again this important peak. In that case, with a much more important average number of measurements. And so it highlights that there is an acoustic transmission between the FM probe and the silicon membrane. And so we can also investigate such transmission numerically. In this case, we're using some 2D axisymmetric simulation in COMSOL, so finite elements method 2. And we have here an FM probe in which you can see both the longitudinal and the transverse wave propagating inside the probe, and just a small silicon substrate sample in contact. And if you look at the field in the silicon sample, when the longitudinal wave arrives at the edge of the AFM probe, you can find again a longitudinal wave, such as the one observed experimentally, but also a transfer wave and also some relay waves. And it happens that some relay waves have been observed in similar geometry. So right now we have the longitudinal, we have the relay, and I think in the future we'll do some experiment to try to detect the transfer wave also. And so much more complicated simulation taking particularly in account the anisotropic silicon will be done soon. And so basically to do a quick summary about the spot, we have investigated both numerically and experimentally the acoustic propagation within the AFM probe. And we have shown that it's sensitive to the material in contact at the edge of the probe, but also that there is some acoustic transmission observed. And so the question now to the future of this project, and of this part of the project, which is still an ongoing research, is can we do some surface impedance imaging using the sensitivity? So just kind of new, we can, as a few measurements have been performed when you have gold disks, such as the one introduced previously, on top of silicon substrate. And so when you look at the time and then at the time before the acoustic echo, you don't see any structures. But now when you are looking at the time of the acoustic structure, at the acoustic echo, you can detect some structures with a lateral resolution that is, for the moment, maybe not the best, but which is better than what you can obtain, which just laser source. And so this is an ongoing work, and the question now is what kind of lateral resolution we can obtain. And so it is known in the AFM community that the probe shape has an important impact on the result you can obtain. And so there is some work to do in that case in this kind of application, either if for the reflection or for transmission, different kind of shape can be interesting and not the same. So there is a lot of numerical simulation that I've started to do, but still ongoing. And the question for the future is, can we develop acoustic microscopy using this coupling? And can we And so either acoustic transmission from the sample to the probe, so we can have transmission and transmission back and do some 3D imaging of sample with nanometric resolution, taking advantage of the very small size of the AFM probe at the edge to have very good lateral resolution. And so can we detect any interface or defects in the sample? And so this is some question for the future and for the future PhD students. And that's the same trench. And so I would like to thank you for your attention for this presentation.